The Iowa bottomlands hit different when the river rose. Jacob Brennan learned that his first spring in 1884, when floodwater crept under his cabin and stayed for months, turning his oak floors into rotting, moldy planks. He had built his foundation exactly the way every settler along the river was told to build it. Level stone piers, perfectly balanced, military manual approved and trusted by builders in 3 counties. By summer, his floorboards were warped beyond repair, and the stench made the cabin nearly unlivable. Across the bottomlands, dozens of families were fighting the same losing battle in cabins built by the book and failing every spring. Over the next 2 years, Jacob quietly applied what neighbors called a stupid, crooked foundation design that kept his cabin bone dry through the worst floods. What did he understand about water flow that every other builder along that river had missed? The pattern held true from the Raccoon River south to the Des Moines. Every spring, the same ritual played out in cabin after cabin, built on what frontier manuals called proper foundation technique. Water would seep under the level stone piers, pool in the shadowed spaces beneath the floorboards, then sit for weeks in the dark humidity. By June, the smell would start. By July, homesteaders would pry up planks to find black rot spreading through joists that had cost them a winter's worth of trading to secure. Jacob Brennan had watched it happen to the Hartwell place in 1882, then the Morrison cabin the following year. Both families had followed the same construction guidelines that Jacob himself had used, the same methods taught by every experienced builder from Illinois to Nebraska. The foundation piers were cut square, set precisely level with a mason's line, and spaced exactly 16 feet on center according to military engineering standards that had proven reliable across a dozen states. The logic seemed unshakable. A level foundation distributed weight evenly, prevented structural settling, and provided convenient access to the storage space underneath where families kept their root cellars and tool sheds. Yet every spring brought the same defeat. The Hartwells had been forced to replace their entire kitchen floor after 18 inches of standing water turned their oak planking into something resembling wet cardboard. The Morrisons lost not just their flooring, but 3 months of preserved meat when mold contaminated their underground storage area. Even families who built their cabins on the highest ground available in the bottomlands found themselves dealing with persistent moisture problems that conventional foundation design seemed powerless to prevent. Jacob's own background should have made him more receptive to alternative approaches than most of his neighbors. His father had been a carpenter who worked contracts for the railroad, and Jacob had spent his teenage years learning not just frontier construction, but the building methods of the immigrant crews who brought techniques from Germany, Scandinavia, and Ireland. Later, when he married Sarah Kessler and settled near her family's land, he had worked alongside Sioux builders who constructed seasonal fishing camps along the river. Their methods bore no resemblance to anything in the military manuals, yet their structures never seemed to suffer the moisture problems that plagued settler cabins. The breaking point came in late April of 1885, when Jacob walked through the wreckage of the Peterson place after the worst flood in local memory. The water had risen high enough to reach the floorboards themselves, but even after it receded, the real damage was happening underneath. Jacob crawled into the space beneath the cabin with a lantern and saw what the level foundation had created, a perfect basin for trapping water. The stone piers formed a grid of miniature dams, and the carefully leveled ground between them had become a series of connected pools where floodwater gathered and stagnated. He could see immediately what needed to change. Water moved downhill when it had somewhere to go, but the standard foundation design gave it nowhere to flow. Every guidebook he had ever read assumed that level meant better, that precise horizontal alignment was the mark of professional construction. But precision was worthless if it created the wrong result. The solution forming in Jacob's mind violated every rule he had been taught about proper foundation work. Instead of fighting to keep water out, he would need to give it a path through and away. Instead of building his foundation as a series of obstacles to water flow, he would design it to channel water in the direction it wanted to go anyway. The concept was so simple it felt almost insulting to the complexity of standard construction methods. When Jacob began explaining his intentions to neighbors, the response was swift and dismissive. Tom Hartwell told him outright that building a tilted cabin was the stupidest thing he had heard since arriving in Iowa. The foundation piers would settle unevenly, Hartwell insisted, and the whole structure would rack itself apart within 5 years. Even Sarah's brother questioned Jacob's judgment, pointing out that every successful cabin in 3 counties used level foundations, and there had to be a reason why experienced builders stuck with methods that had proven themselves across generations of frontier construction. The criticism stung partly because Jacob understood the logic behind it. A foundation that was not level did present genuine challenges for construction. Door frames would need to be shimmed, floorboards would require careful measurement and cutting, and the visual appearance would announce to everyone that this cabin had been built differently than the accepted standard. In a community where conformity often meant survival, standing out carried real social costs. But Jacob had crawled under too many failed foundations to ignore what his own eyes had shown him. The standard method was not working in this particular place, with this particular soil, facing these particular flood patterns. What worked in Illinois or Missouri was failing in the Iowa bottomlands for reasons that seemed obvious once you stopped assuming that established practice was automatically correct practice. By autumn of 1885, Jacob had made his decision. He would build his new cabin with a foundation that sloped deliberately toward the river, giving floodwater a clear path away from his home instead of trapping it underneath. The neighbors could call him foolish if they wanted. Come spring, the water would settle the argument. The first challenge Jacob faced was calculating the exact degree of slope needed to move water effectively without creating structural problems. Too little incline, and the water would still pool in low spots. Too much, and the cabin would look obviously crooked, potentially causing issues with door alignment and interior furnishing. Working with Heinrich Müller, a German stonemason who had helped build drainage systems in flood-prone areas of the Rhine Valley, Jacob settled on a 2-inch drop from the back wall to the front over the cabin's 24-foot depth. Heinrich brought knowledge of European foundation techniques that used controlled slopes for water management, but it was Jacob's conversations with old Joseph Crow Feather that provided the crucial insight into how to execute the design properly. The elderly Sioux builder had constructed dozens of seasonal structures along the river bottoms, and his people had long understood that fighting water was futile while directing it was practical. Joseph showed Jacob how to read the natural drainage patterns in the soil itself, identifying the subtle channels where water wanted to flow, even when the land appeared flat to untrained eyes. The construction began in late October of 1885 with the cutting and placement of foundation stones. Instead of using the standard method of setting each pier to identical height, Jacob established his baseline at the rear of the cabin site and measured each successive row of piers to be precisely 1/2 inch lower than the row behind it. This created the gradual slope while maintaining the necessary support strength at each point. The stones themselves came from a quarry 12 miles upriver, chosen specifically for their flat surfaces and resistance to frost damage. Each stone pier measured 18 inches square and stood 30 inches above the ground level, with an additional 18 inches buried below the frost line. The spacing remained at the standard 16 feet on center, but Jacob introduced a modification he had learned from Joseph Crow Feather. Small channels carved into the top surface of each stone that would guide any water that did reach the foundation level toward the front of the structure. These 1/4-inch deep grooves were invisible once the floor joists were in place, but they provided insurance against water accumulation, even in the most severe flood conditions. The floor joist installation required careful adjustment to accommodate the intentional slope while maintaining structural integrity. Jacob cut each joist to standard 8-inch depth, but shimmed the rear connections to ensure the joists themselves remained level even as the foundation dropped toward the front. This meant that the interior floor would be perfectly flat while the foundation underneath followed the deliberate grade that would channel water away from the structure. Heinrich contributed a technique from German construction called underpinning, where small drainage channels were dug between foundation points to create positive water flow even during the most extreme flood events. These channels, only 6 inches wide and 4 inches deep, connected each row of foundation piers and ensured that water reaching any point under the cabin would find a clear path toward the front slope and away from the building. The winter of 1885 to 1886 tested the structural soundness of the sloped foundation through months of freeze and thaw cycles that could destroy improperly built stonework. Jacob monitored each pier carefully, checking for signs of movement or settling that would indicate problems with his unconventional approach. The foundation remained solid, with no detectable shifting even during the harsh February when temperatures dropped below zero for 12 consecutive days. Sarah Brennan initially worried about the practicality of living in a cabin built on an intentionally uneven foundation. Would furniture slide toward the front? Would water spill from buckets? Would the visual effect make guests uncomfortable? Jacob addressed these concerns by demonstrating that the slope was too gradual to affect daily life inside the cabin. A marble rolled across the floor would eventually reach the front wall, but so slowly that the movement was barely perceptible. The 2-inch difference over 24 feet created an angle of less than 1 degree, far below the threshold of human perception in normal activities. When the spring floods of 1886 arrived in early April, they provided the definitive test of Jacob's foundation design. The water rose higher than it had in 5 years, reaching a level that flooded not just the space under cabins, but the first floor of several structures built too close to the river. Jacob's cabin sat on ground that put it safely above the floodwater line, but the real test came in what happened underneath. While neighboring cabins with level foundations became inadvertent reservoirs that held stagnant water for weeks after the flood receded, Jacob's sloped foundation performed exactly as designed. The water flowed through the space under his cabin in a matter of hours, following the channels Heinrich had dug and the natural grade Jacob had built into his stone piers. By the time Tom Hartwell was still pumping water out of his foundation space, Jacob's crawl space was completely dry and showing no signs of the moisture problems that plagued every other cabin in the bottoms. The success was measurable and immediate. Jacob's foundation space remained dry throughout the summer, while his neighbors dealt with humidity levels that made their root cellars unusable and created perfect conditions for the wood rot that would require expensive repairs by autumn. The 2-inch slope had solved a problem that standard construction methods could not address, proving that sometimes the unconventional approach was the only practical solution. The success of Jacob's foundation design led him to question other aspects of conventional cabin construction, particularly the standard approach to wall insulation that left most Iowa settlers shivering through winter months while burning through firewood at an unsustainable rate. The typical frontier cabin used single-thickness log walls with basic chinking between the logs, a method that worked adequately in milder climates but proved insufficient against the harsh temperature swings of the Iowa bottomlands. Jacob had experienced this problem firsthand in his previous cabin, where indoor temperatures on January mornings often dropped to within 15 degrees of the outdoor air, despite keeping a fire burning through the night. The single log walls conducted heat directly to the outside, creating a constant battle between the fireplace and the bitter cold that penetrated through every gap and joint. Even worse, the same walls that failed to keep heat in during winter became heat traps during summer, making the interior unbearably hot during the humid Iowa summers. Joseph Crow Feather introduced Jacob to a wall construction technique that his people had used for generations in their permanent winter lodges. Instead of relying solely on wood for insulation, the Sioux builders created thick earthen walls using a mixture of clay-rich soil, dried grass, and animal hair that formed an effective barrier against both heat loss and moisture penetration. The technique required no expensive materials and used resources available within walking distance of any cabin site. The earthen wall system began with a framework of vertical posts set every 4 feet around the cabin perimeter. Between these posts, Jacob wove a lattice of willow branches and split oak strips that would hold the earthen mixture in place as it dried. The clay mixture itself consisted of 3 parts local soil to 1 part chopped prairie grass, with a handful of cattle hair added to each bucket to bind the mixture and prevent cracking as it cured. Heinrich Muller contributed his knowledge of European cobhouse construction, which used similar principles but with more refined techniques for achieving consistent thickness and weather resistance. The German approach involved applying the earthen mixture in successive layers, allowing each coat to dry partially before adding the next. This prevented the thick walls from developing the deep cracks that could compromise their insulating properties during the freeze-thaw cycles of Iowa winters. The first layer, applied directly to the willow lattice, consisted of the coarsest mixture with the highest proportion of chopped grass and hair-binding agents. This base layer was worked by hand into a thickness of 4 inches, pressed firmly into the lattice framework to ensure strong adhesion. After 3 days of drying time, Jacob applied a second layer of finer mixture that brought the total wall thickness to 7 inches at most points around the cabin. The final layer used clay that had been strained to remove stones and large organic matter, mixed with fine sand that Heinrich obtained from a creek bed 5 miles upstream. This finishing coat provided weather protection and created a smooth interior surface that could be whitewashed or left natural depending on preference. The total wall thickness of 8 to 9 inches created an insulating barrier that far exceeded anything achievable with conventional log construction. Temperature testing during the winter of 1886 to 1887 demonstrated the dramatic effectiveness of the earthen wall system. Using a thermometer that Heinrich had brought from Germany, Jacob recorded interior temperatures that remained consistently 25 degrees warmer than outdoor readings, even during the coldest nights when neighboring cabins struggled to maintain livable conditions. More importantly, the thick walls retained heat for hours after the fire died down, eliminating the need for constant wood feeding that exhausted the fuel supplies of families using standard construction. The earthen walls also solved moisture problems that plagued conventional cabins throughout the humid Iowa summers. The clay mixture absorbed excess moisture from indoor air during humid periods and released it gradually when conditions became drier, creating a natural humidity control system that prevented the condensation problems common in tightly chinked log cabins. This moisture buffering effect reduced the mold and mildew issues that made many frontier homes uncomfortable and unhealthy during the wet months. Sarah Brennan initially worried about the appearance and durability of walls made from mud and grass, fearing they would crumble during heavy rains or develop cracks that would allow wind and moisture to penetrate the interior. Jacob addressed these concerns by demonstrating the strength of properly mixed earthen construction. A section of test wall built behind the cabin withstood direct application of water from a bucket without showing signs of erosion or structural weakness. The construction process required careful timing to take advantage of optimal weather conditions for drying and curing. Jacob began work on the walls in late May, when spring rains had ended but summer heat had not yet created conditions that would cause the earthen mixture to dry too quickly and crack. Each section of wall needed 4 to 6 days of dry weather to cure properly, so Jacob planned the work in segments that could be completed between rain periods. The earthen walls proved their value during the harsh winter of 1887, when temperatures dropped below zero for 3 weeks straight and neighboring families burned through their entire winter wood supplies by February. Jacob's cabin required 40% less firewood to maintain comfortable interior temperatures, and the steady warmth allowed his family to use their living space productively for activities like sewing and food preparation that became impossible in poorly insulated cabins. By spring, word of Jacob's wall construction had spread throughout the Bottomlands community. Families who had struggled with heating costs and summer heat retention began asking for details about the earthen wall technique. The method's effectiveness was undeniable, measured not just in comfort, but in the practical economics of firewood consumption and the extended usability of interior space during extreme weather periods. The combination of the sloped foundation and the insulating earthen walls created a cabin that performed fundamentally differently than conventional frontier construction. Where standard building methods created an ongoing struggle against water, cold, heat, and humidity, Jacob's integrated approach worked with natural forces to create comfortable living conditions year-round while reducing the resources required for heating and maintenance. Having solved the foundation drainage and wall insulation challenges, Jacob turned his attention to the cabin's most vulnerable element, the roof system that would determine whether his innovative construction would survive Iowa's punishing cycle of spring rains, summer storms, and winter snow loads. Standard frontier roof construction used modest slopes that made construction easier, but created persistent problems with water penetration and structural stress during heavy snow accumulation. Most cabins in the Bottomlands used roof pitches of 4 inches of rise for every 12 inches of horizontal run, a shallow angle that allowed builders to work safely during construction and required less lumber for the rafter system. However, this gentle slope meant that rainwater moved slowly across the shingles, increasing the likelihood of wind-driven moisture finding its way through gaps in the roofing material. Even worse, the low angle provided insufficient encouragement for snow to slide off naturally, creating dangerous loading conditions that had collapsed 3 roofs in the area during the severe winter of 1884 to 1885. Joseph Crow Feather had observed these failures and shared with Jacob the approaches people used for their permanent winter structures. Sioux builders constructed roofs with much steeper angles, typically rising 8 to 10 inches for every 12 inches of horizontal distance. This dramatic pitch served multiple purposes. Rain and melting snow moved rapidly off the roof surface, reducing moisture penetration. Snow loads were shed naturally rather than accumulating to dangerous weights. And the steeper angle created additional interior space in the loft area that could be used for storage or sleeping quarters. The challenge lay in adapting the steep roof concept to log cabin construction while maintaining structural integrity and weather-tight performance. Jacob worked with Heinrich Müller to design a rafter system that could support the increased stresses created by a steep pitch, while using locally available timber cut to precise specifications. The solution involved cutting rafters from straight-grained oak trees that had been felled during the previous winter and seasoned through the spring and summer months. Each rafter measured 8 inches in depth and 3 inches in thickness, cut from timber that Heinrich selected specifically for its freedom from knots and consistent grain structure. The rafters were spaced exactly 24 inches on center, closer than the 30-inch spacing typical in standard construction, to distribute the roof loads more evenly and prevent sagging under snow weight. The steeper angle meant that each rafter had to be precisely cut to maintain consistent roof line and proper bearing on both the wall plates and the ridge beam. The ridge beam itself represented a critical departure from conventional practice. Instead of using a single timber running the length of the cabin, Jakob and Heinrich constructed a built-up beam using 3 parallel oak timbers bolted together with iron hardware that Heinrich forged in his own blacksmith shop. This composite ridge beam measured 12 inches in total depth and provided the structural strength necessary to support the steeper roof angle without sagging over time. Shingle installation on the steep roof required techniques that Jacob learned from Scandinavian immigrants who had settled 20 miles north of the bottomlands. These builders used a system of overlapping cedar shingles installed in courses that began at the bottom edge of the roof and worked upward, with each course covering at least half the length of the shingles in the course below it. The steep angle meant that water would flow rapidly across this overlapped surface, but it also required more careful attention to wind-driven rain that could work its way under inadequately secured shingles. The cedar shingles themselves came from trees that grew in the timber stands along the upper reaches of the Des Moines River. Jacob spent 2 weeks in late summer selecting and cutting cedar trees that showed the straight grain and natural rot resistance necessary for long-term roof performance. The shingles were split by hand using a froe and mallet, creating pieces that measured 18 inches in length and varied from 4 to 6 inches in width depending on the natural grain of each tree. Installation began in September of 1886 when weather conditions provided the dry periods necessary for proper shingle placement. Each shingle was secured with 2 hand-forged iron nails positioned 1 inch from each edge and 6 inches up from the bottom edge. The steep roof angle meant that Jacob and Heinrich had to work with ropes and climbing equipment to maintain safe footing while positioning and nailing each piece. But the same angle that made installation challenging would prove critical for the roof's long-term performance. The first test came during the October storm of 1886, when 3 days of wind-driven rain challenged every roof in the Bottomlands community. Jacob's steep roof performed exactly as the design intended, shedding water so rapidly that no moisture penetrated the interior, even during the most intense periods of the storm. Neighboring cabins with conventional roof angles experienced multiple leaks that required buckets positioned throughout their interiors to catch dripping water. Snow loading during the winter of 1886 to 1887 provided an even more dramatic demonstration of the steep roof's advantages. When 2 feet of wet snow fell during a 3-day period in January, the accumulation on Jacob's roof lasted only until the sun emerged. The steep angle and smooth cedar surface allowed the entire snow load to slide off in large sections, leaving the roof clear and eliminating the weight that continued to stress conventional roofs throughout the winter months. Temperature measurements inside the cabin during this period showed another unexpected benefit of the steep roof design. The increased interior volume created by the high peak provided space for warm air to rise and circulate, creating a natural convection system that distributed heat more evenly throughout the living space. The loft area remained consistently warmer than the main floor, providing comfortable sleeping quarters during even the coldest nights. The drainage system extended beyond the roof itself to include carefully positioned gutters and downspouts that directed rainwater away from the foundation area. Jacob carved wooden gutters from split logs and positioned them to collect runoff from the steep roof and channel it through wooden downspouts that carried the water at least 10 feet away from the cabin's foundation. This completed the water management system that began with the sloped foundation and continued through the roof design. By spring of 1887, the integrated approach to water management had proven its effectiveness through a full year of seasonal challenges. The steep roof had shed snow and rain without allowing moisture penetration. The drainage system had protected the foundation area from water accumulation, and the overall structural integrity remained solid despite the unconventional construction methods that neighbors had initially criticized as unnecessary and impractical. The ultimate test of Jacob's integrated building system came during the catastrophic spring of 1888, when unprecedented flooding combined with late-season snowstorms to create conditions that destroyed or damaged more than half the cabins in the Iowa bottomlands. The disaster began in early March, when unusually heavy snowfall was followed by 3 days of warm rain that created rapid snowmelt and sent every creek and river in the region over its banks simultaneously. The floodwaters rose higher than anyone in the area had ever recorded, reaching levels that put water not just under cabin foundations, but actually flowing through the main floors of structures built too close to the river channels. Even cabins positioned on higher ground found themselves surrounded by standing water that persisted for nearly 2 weeks after the initial flood peak passed. The extended duration of the flooding created the most severe test possible of foundation drainage systems and moisture management techniques. Jacob's cabin became an unofficial headquarters for flood relief efforts precisely because it remained completely habitable throughout the disaster. While neighboring families crowded into the few buildings that stayed dry, Jacob and Sarah provided shelter and coordination space for rescue operations. The integrated performance of the sloped foundation, earthen walls, and steep roof created an environment that not only stayed dry but maintained comfortable living conditions even when surrounded by flood conditions that made most other structures uninhabitable. The contrast was measurable and dramatic. Tom Hartwell's cabin, built with conventional level foundations just 2 years earlier, accumulated 18 inches of standing water in the crawl space that remained for 6 weeks after the flood receded. The prolonged moisture exposure caused complete failure of the floor joists, requiring demolition and rebuilding of the entire structure at a cost that forced the Hartwell family to abandon their homestead and return to Illinois. Heinrich Müller documented the flood's impact by conducting systematic inspections of damaged buildings throughout the Bottomlands community. His survey revealed that cabins built with standard construction methods experienced damage ranging from minor moisture problems to complete structural failure. The average cost of flood-related repairs exceeded $200 per cabin, representing nearly a full year's income for most frontier families. The economic implications extended beyond immediate repair costs to include lost agricultural productivity when families had to focus on rebuilding rather than spring planting, and reduced property values that made it difficult for damaged homesteads to attract new buyers or secure credit for reconstruction. Several families abandoned their claims entirely, creating a pattern of settlement failure that threatened the viability of the entire Bottomlands community. Jacob's cabin required no flood-related repairs of any kind. More significantly, the earthen walls actually improved in durability after the flooding because the moisture content in the air during the extended wet period allowed the clay mixture to complete its curing process, creating walls that were harder and more weather-resistant than when originally constructed. This unexpected benefit demonstrated how indigenous building techniques had evolved specifically to work with, rather than against, environmental extremes. Word of Jacob's construction success spread beyond the immediate area through Heinrich's connections with German immigrant communities across Iowa and neighboring states. The stonemason began incorporating elements of the sloped foundation design into his own construction projects, adapting the water management principles to different soil conditions and flood patterns. By 1890, builders throughout the upper Midwest were experimenting with deliberate foundation slopes and integrated drainage systems based on the techniques proven effective in the Iowa bottomlands. Joseph Crowfeather's contribution gained recognition when territorial officials conducting flood damage assessments learned about the indigenous building methods that had informed Jacob's wall and roof construction. The territorial engineer, a man named Charles Morrison, who had trained at West Point, spent 3 days studying Jacob's cabin and documenting the construction techniques for potential inclusion in official building guidelines for frontier settlements in flood-prone areas. Sarah Brennan played a crucial role in documenting and teaching the construction methods to other frontier women whose families were rebuilding after the flood. She organized work parties that demonstrated the earthen wall construction process, showing how families could build superior insulation using local materials and cooperative labor, rather than expensive imported lumber and hardware. These teaching sessions created a network of knowledge sharing that spread the techniques far more effectively than formal instruction manuals. The steep roof design proved especially influential among Scandinavian immigrants who recognized similarities to building techniques from their homeland. Erik Johansson, a Norwegian carpenter working in the Des Moines area, adapted Jacob's roof pitch and shingle installation methods to create a hybrid approach that combined the steep angle advantages with traditional Norwegian timber framing techniques. This cross-cultural exchange created building methods that were superior to either tradition used separately. By 1892, elements of Jacob's integrated construction approach had been incorporated into the official territorial building codes for flood-prone areas. The new regulations required foundation drainage considerations, specified minimum roof pitches for areas with heavy snow loads, and recommended earthen wall construction for settlers who could not afford imported lumber. The transformation from experimental technique to official standard demonstrated how practical innovation could reshape accepted building practices when proven effective through real-world testing. The long-term durability of Jacob's cabin provided continuing evidence of the construction method's effectiveness. When Jacob sold the property in 1898 to move his family to town, the cabin remained in excellent structural condition after 12 years of Iowa weather extremes. The new owners, a young couple named David and Martha Klein, reported that the cabin required no major maintenance for the first 5 years of their occupancy, a remarkable performance record for frontier construction. Jacob's construction legacy extended through the technical training he provided to his sons, who became builders in their own right and carried the integrated construction principles to homesteading communities throughout Kansas and Nebraska in the 1890s. The techniques adapted successfully to different climates and soil conditions, proving that the underlying principles of working with natural forces rather than against them had universal application in frontier construction. The transformation of the Iowa bottomlands building practices demonstrated how indigenous knowledge, immigrant expertise, and practical experimentation could combine to create construction methods superior to any single tradition. Jacob's success challenged the assumption that conventional wisdom represented the best available knowledge, proving instead that careful observation and willingness to integrate diverse approaches could solve problems that standard methods could not address.